Day 42 for the series. It's been a while, but let's continue. 1 second. Yeah. A global view of the historical record. As financial markets around the world grow and become more transparent, US investors look to improve diversification by investing internationally. Foreign investors that traditionally used US financial markets as a safe haven to supplement home country investments also seek international diversification to reduce risk. The question arises as to how historical US experience compares with that of the stock markets around the world. Figure 5.8 shows a century plus long history, 1900 to 2015, of average excess returns in 20 stock markets. The mean annual excess return across these countries was 7.40%, and the median was 6.50%. The United States is roughly in the middle of the pack with a historical risk premium of 7.55%. Similarly, the standard deviation of returns in the US, not shown, was just a shade below the median volatility in these other countries. So the US performance has been pretty much consistent with international experience. We might tentatively conclude that the characteristics of historical records in the US can also can serve as a rough indication of the risk return trade-off in a wider range of countries. Of course, we've seen that there is tremendous variability in the year by year returns, and this makes even long term average performance a very noisy estimate of future returns. There is an ongoing debate as to whether the historical US average risk premium of large stocks over T bills of 8.3% is a reasonable forecast for the long term. This debate centers around two questions. First, do economic factors that prevailed over the historical period 1926 to 2015 adequately represent those that may prevail over the forecasting horizon? Second, is average performance from the available history a good yardstick for long-term forecasts? So we will return to these questions again later in the text. 5.9, normality and long-term investments. Based on historical experience, it may be reasonable to treat short-term stock returns as approximately described by a symmetric normal distribution. But even if that is so, long-term performance cannot be normal if R1 and R2 are the returns in two periods and each have the same normal distribution. Then the sum of the returns R1 plus R2 would be normal. But the two-period compound return is not the sum of the two returns. Instead, invested funds would compound to 1 plus R1 plus into 1 plus R2, which is not normal. This is more than a theoretical point. The shape of the distribution changes noticeably as the investment horizon extends. To illustrate, suppose that you invest $100 in a stock with an expected monthly return of 1%, but there is a dispersion around the expected value. With equal probability, the actual return in any month will exceed the mean by 2%. For a return of 1% plus 2% equal to 3%, or fall short by 2%. For a return of 1% minus 2% equals to minus 1%. These two possible monthly returns, minus 1% or minus 3%, are thus symmetrically distributed around the 1% mean. Now let's look at the distribution of the portfolio value at the end of several investment horizons. Figure 5.9 shows the results. After 6 months, panel A, the distribution of possible values is beginning to take on the shape of a familiar bell-shaped curve. As we observed earlier, the mid-range values are more likely because there are more paths that take us to these outcomes. After 20 months, panel B, the bell-shaped distribution is even more obvious, but there is already a hint that extremely good cumulative returns with possible stock prices extending to $180 for a cumulative gain of 80% are more prevalent than extremely poor ones. Notice that the worst possible outcome is $82, implying a total loss of only 18%. After 40 months, panel C, the asymmetry in the distribution is pronounced. This pattern emerges because of compounding. The upside potential of the investment is unlimited, but no matter how many months in a row you lose 1%, your funds cannot drop below zero. So there's a floor on worst possible performance. You can't lose more than 100% of your investment. After 40 months, the best possible stock value is 100 into 1.03 to about 40, which is equal to $326 for a total gain of 226%. But the worst possible outcome is 100 into 10.99 to about 40, which is equal to $66.9 for a cumulative loss of 33.1%. When the probability distribution in figure 5.9 is of bell shape, it is distinctly asymmetric bell, with a positive skew, and the distribution is clearly not normal. In fact, the actual distribution approaches the log normal distribution. Log normal means the log of the final portfolio value, LNWT, is normally distributed. Does the result invalidate the simplifying assumption of normally distributed returns? Fortunately, there is a simple fix for this conundrum. Instead of using effective and annual returns, we can continuously we can use continuously compounded returns. If the continuously compounded returns in 2 months are RCC1 and RCC2, then invested funds grow by a factor of RCC1 in the first month and exponential RCC2 in the second month. Where exponential is the exponential function. The total growth in the investment is thus exponential RCC1 into exponential RCC2 is equal to exponential RCC1 plus RCC2. In other words, the total 2-month return expressed as continuously compounded rate is the sum of the 1-month returns. Therefore, if the monthly returns are normal, then the multi-month returns will also be normal. Thus, by using continuously compounded rates, even long-term returns can be described by the normal distribution. Moreover, if returns have the same distribution in each month, then the expected 2-month return is just the twice expected 1-month return, and if returns over time are uncorrelated, then the variance of the 2-month return is also twice that of the 1-month return. We can generalize from this example to arbitrary investment horizons, which we will call T. If the expected per period continuously compounded return is RCC, then the expected cumulative return after an investment period of T periods is expected RCCT. And the expected final value of the portfolio is expected value of portfolio equals to original value times exponential ERCCT. The variance of the cumulative return is also proportional to the time horizon variance equals to T into variance RCC. Therefore, the standard deviation grows in proportion to the square root of the time horizon. Short run versus long run risk. Our results on the risk and return of investments over different time horizons appear to offer a mitigation of investment risk in the long run, because expected return increases with horizon at a faster rate than standard deviation. The expected return of a long-term risk investment becomes even larger relative to its standard deviation. Figure 5.9, frequency distribution of final portfolio value after a different number of months. Initial investment equals to $100. In any month, the portfolio value will increase by 3% or fall by 1% with equal probability. Does this mean that investments are less risky when horizons are longer? To see why many people believe so, consider the following example. The probability of a shortfall is an incomplete measure of an investment risk. This probability does not take into account the size of potential losses, which for some of the possible outcomes, however unlikely they may be, amount to near ruin. The worst case scenario for the 30-year investment are far worse than for the 1-year investment. You can see this point vividly by comparing the VAR value at risk or something, the investment on different horizons. Investment risk in the short run and the long run. Suppose that investment returns are independent from year to year with an expected continuously compounded return of 0.05 and standard deviation of 0.3. Let's look at the properties of investment horizons of 1, 10, and 30 years. These are laid out in table 5.5. The mean average annual return is 5% regardless of the horizon, but the mean cumulative return rises in direct proportion to T. The standard deviation of the cumulative return rises in proportion to the square root of T. Next, we look at the probability that the cumulative return will be negative. In other words, the investor will suffer a loss for the 1 year